Welcome to our 135 presentation on fault locating with traveling waves by me, Alexis Aiken, and Jesse Harkness. Here I will talk about faults and the type of faults that happen in power systems. Electrical faults are deviations of voltages and currents from their nominal values. When a fault occurs, extensively high currents flow which cause damage to the equipment. In power systems, there are two types of faults: a symmetrical fault and an unsymmetrical fault. A symmetrical fault would be a balanced fault where phase A, B, and C are all connected to ground through an external impedance. And unsymmetrical faults would be single line to ground where one phase is connected to ground, double line to ground when two phases are connected to ground, and a double line where two phases will be interconnected with each other through an external impedance.
Once a fault occurs, it's critical to locate and repair that fault. One method to locating a fault would be the impedance-based method. The impedance-based method uses the voltages and currents to make equivalent calculations and locate the fault. The accuracy for an impedance-based method falls within the 0.5 to 2% range. For example, if we take a 300,000 meter transmission line, using that method with an error of about 1% will leave a lot of ground to cover, which is 6,000 meters or 20 tower lengths. On the other hand, we have traveling waves. The traveling waves method is based on a measurement of time that it takes to reach the end of the transmission line. If we look at the same transmission line distance, traveling waves can predict a fault up to 300 meters or 1 tower length. First method for finding faults using traveling waves would be the double-ended method. This makes use of synchronized observation stations with each one placed on each side of the transmission line. They must be synchronized by a GPS clock or something equally reliable. As you can see on the slide, the equation for a double-ended method seems rather complicated. It consists of the transmission line length, the time of arrival at both ends of the line, and the velocity of the wave traveling through the medium. In addition to being complicated, it's costly as well because you have to set up two observation stations on each side of the line. And it doesn't work for complex topologies, for example tapped lines in the middle or transformers. Another method used to locate faults using traveling waves would be the single-ended method. This method is much simpler because it only requires one observation station at one side of the transmission line. Looking at the equation of the single-ended method, we can see that it's a much simpler equation. It consists of the speed of light factor, which is the approximate amount of time to adjust when traveling through that medium, the speed of light, and the time between the reflected waves. It is much more effective than a double-ended method and cheaper to implement. The basics of traveling waves comes down to reflection and inversion of either voltage or current. Traveling waves are associated to the voltage reflection coefficient known as gamma. Gamma consists of the termination impedance at the end of the line and the characteristic impedance of the line. Here we have an example of a transmission line that has been energized and waves are traveling to the end of the line. Here, in this condition, we see that the termination impedance is greater than the characteristics impedance. Therefore, we get a perfect voltage reflection on the line. Then again, we see in this condition that the sum of the currents must add up to 0. Therefore, we get a current inversion on the line as well. This is known as an open circuit termination impedance,
where under this condition we see that gamma equals 1 and the termination impedance is infinite. Here we see another example of traveling waves. The same equation in the previous slide applies to this example. In the previous slide, we saw that we had a voltage reflection and a current inversion. In this example, we see that the termination impedance is less than the characteristic impedance of the line. Therefore, we get a voltage inversion for this example. Notice that the polarity is positive flowing to the end of the line, and the polarity switches flowing back to the source. In this example, we get a current reflection on the line under this condition. To satisfy this example, we see that the sum of the voltages must add up to 0. Therefore, for this example, it's considered to be a short circuit. For this condition, gamma equals -1, and the termination impedance is 0, or somewhat close to 0.
As a fault happens somewhere in the middle of a transmission line, the voltage comes out of the fault with a phase shift, heading towards both sides of the transmission line substations. When it hits the substation tends to have a lower impedance than the characteristic impedance of the transmission line due to parallel connections coming off of it. So the voltage wave has another phase shift as it goes back towards the fault again. This pattern continues, and the voltage flips its phase each time it reflects from the fault to the substation back and forth again. So the phase always changes. This makes voltages hard to use as a reference point. Current waves, on the other hand, come out of the fault in the same direction that they went into the fault, because the characteristic impedance of the line being higher than the fault causes it to reflect perfectly. So as you can see in this image, the current wave that went into the fault comes back out with a positive phase shift on this side, and on the other side, because it was coming back this direction, negative, you see it bounces back off perfectly this direction, still negative. So it maintains its polarity the same as it bounces off these different points all the way back to the first station that's making the observations. Due to this feature with the current waves and it always maintaining its polarity, you can tell where it originated from. If it comes from this side of the fault, it'll have a positive polarity. If it came from this side and traveled back over here, it'll have a negative polarity. This is why current traveling waves are used to locate faults. In the event that a fault happens on the line closer to the local station, as it's called in this case, on the left side of the transmission line, the first two traveling waves to hit that recorder on that side of the line will both be from that side of the fault. And for that reason, they will both have the positive polarity to them, and the time between the two strikes of the traveling wave will actually be 2 times the distance to the fault, as can be seen here. In the event that a fault happens towards the opposite or remote station of the transmission line, the 2 first traveling waves that strike off of our recorder at the local station will be of opposite polarity. The first will be positive from our side of the fault, and the second will be the reflected wave off of the remote station back to our side at the local station. For this reason, we'll see a positive polarity wave followed by a negative polarity wave, and the time between those 2 waves striking will be 2 times the distance from the fault to the remote station. With what we've just learned in mind, we take a look at a case study by PG&E on their Humboldt Trinity 115 kilovolt line. There was a fault somewhere along the 68.9 mile long line. They decided to try to use traveling waves to detect a fault as a way to avoid the use of expensive equipment like a helicopter and a search crew to try to find the source of the problem. As can be seen by the data provided by PG&E's recorder at their local station during the fault, there was a large swing in positive current followed by another one in negative current. This would lead us to believe that there was a fault closer to their remote station on the line. Due to the precise recording of PG&E's equipment, the fault could be seen at a level of 253.4 microseconds from the peak of the spike in current down to the negative swing. Using this information with the factor of the speed of light traveling through the medium of the transmission line times the speed of light itself divided by 2, they were able to calculate the distance between the remote station to be 23.2 miles from the location of the faults. The actual distance as they went out and found the problem was 23.5 miles from the Humboldt side of the station. This is a great accuracy and saves a lot of money in trying to find the source manually with people on foot, helicopters, that sort of thing. Due to the precise recording of PG&E's equipment, the fault could be seen at a level of 253.4 microseconds from the peak of the spike in current down to the negative swing. Using this information with the factor of the speed of light traveling through the medium of the transmission line times the speed of light itself divided by 2, they were able to calculate the distance between the remote station to be 23.2 miles from the location of the faults. The actual distance as they went out and found the problem was 23.5 miles from the Humboldt side of the station. This is a great accuracy and saves a lot of money in trying to find the source manually with people on foot, helicopters, that sort of thing.